Okay, so let's continue next with exercise 66. Here we are given a field f, and it's given that the characteristic of f is not 2. That means it's something else, it's not 2. And also it's given that the non-zero elements in the field form a cyclic group under multiplication. We already know that they form a group under multiplication, but it's additionally given that this group is cyclic. Then we have to prove that f is finite. So let's see the solution. And the proof is by contradiction. We will suppose that f is infinite and then arrive at some contradiction. Suppose f is infinite. Then the cyclic group that is the non-zero, the group of non-zero elements in F under multiplication, of course, to indicate that fact, let's just write this as a pair, as an ordered pair, where the first coordinate is the set and the second one is the binary operation. And it's given that this group is cyclic, but now because of our supposition it has become an infinite cyclic group. Because we have supposed that f is infinite, so removing just this zero element from f will also keep it infinite, is infinite. But from group theory we know that there is precisely one infinite cyclic group up to isomorphism, and that is the additive group of integers. So this group is isomorphic to the cyclic group Z plus, that is the additive group of integers. Okay. Now we use the fact that the characteristic of this field is not 2, since the characteristic of f is not 2, we have -1 not equal to 1. The additive inverse of 1 will not be equal to 1 itself, because otherwise we will have 2 equal to 0, but that would just simply imply that the characteristic of the field is 2. So that means the element -1, of course this -1 we know is not equal to 0. So this element -1 actually belongs to this group, just like 1 belongs to the group. So -1 is an element in this group that is different from the identity element in the group, which is 1. Also, if you calculate this power of -1, then you know that it's 1. So the order of -1 in our multiplicative group is 2. The first power of minus 1 is not identity, but the second power is. So that's why the order is 2. But this group, on the other hand, does not have any element of order 2. So that is a contradiction, because isomorphic groups are essentially group theoretically exactly the same thing, but the group lacks elements of order 2. This is a contradiction. So our supposition is wrong. That means, because it's the supposition from where this whole thing is coming. i.e., so what was our supposition? That f is infinite. So it's wrong. So because of that, this must be finite, and that's what we wanted to show. So that is the solution. Next, #67. Suppose that capital D is an integral domain and that phi is a non-constant function from D to the non-negative integers and there are additional restrictions on phi too, such that phi of xy is equal to phi of x times phi of y. That means phi preserves multiplication. If x is a unit in D, with all these things, if x is a unit in D, then we have to show that phi of x is equal to 1. Okay, so let us see all the things once more. D is an integral domain and phi is a function whose domain is D, and the values that phi take on are non-negative integers. Also it's given that phi has this property. Then if x is an element in D which is a unit, that means x has a multiplicative inverse also in D, so that if we take the product of x and that element, that multiplicative inverse, you are going to get the unity 1 in D. Then we have to prove that the phi image of x is equal to 1. Okay, so we start the solution like this. Suppose phi of x is equal to 0. Okay, we want to prove, we have to show that phi of x is 1, but let's see what happens if we suppose that phi of x is 0. Then phi of 1 is equal to phi of x inverse. Since x is a unit, so its inverse exists in D, and x inverse is the unity 1 in D. This one, you should understand that this one is not the real number 1, but it's the unity in the integral domain D. Now you use this property. This is phi of x times phi of x inverse. But by our supposition phi of x is 0, so we are getting 0. Right, so our supposition has led us to the conclusion that phi of 1 is 0. But then for any element y in our integral domain, if we now calculate phi of y using this trick, y is also the unity 1 times y, and we use the multiplicative nature of phi to write this as phi of 1 times phi of y. But phi of 1 is 0, so you get 0. But something has gone wrong. What has gone wrong is that we have ended up proving that phi of y is equal to 0 regardless of what y is. That means phi is constantly 0 throughout the integral domain D, but it's given that phi is a non-constant function, so that has been contradicted. So we write like this, which contradicts the non-constant nature of phi. So our supposition is wrong. i.e., so that means phi of x cannot be 0. Okay, so this is a conclusion, and now we are going to use this in another calculation. Now let's calculate phi of 1 with this new knowledge. Phi, okay, should we calculate phi of 1 or, oh, that will come afterwards. But let us now again start with phi of x, but now with this new knowledge that it's non-zero. and we proceed like this. X is 1x, that is phi of 1 times phi of x. Since phi of x is non-zero, from this equation phi of x equal to phi of 1 times phi of x, we get phi of 1 equal to 1. How? Because keep in mind that these are non-negative integers. So actually we are looking at integers. The phi values are all integers. And if you know on top of this that phi of x is non-zero, then you can cancel phi of x from both sides and have phi of 1 equal to 1. So 1 is equal to phi of 1, that is equal to phi of x times x inverse, which again using the multiplicative nature of phi becomes phi of x times phi of x inverse. Okay, so what is it that we have finally got? The product of these two non-negative integers has to be equal to 1. Actually both of them should be positive, because if any one of them is actually 0, we will have 0 equal to 1, which is false. So you are looking at two positive integers whose product is equal to 1. So both of them have to be equal to 1. Since phi of x and phi of x inverse are positive integers, we must thus have phi of x equal to 1. Phi of x inverse is also 1, but we don't need that. Okay, so that's how we ended up proving that phi of x is 1. So there the solution ends. Next, let f be a field of order 32. That means there are 32 elements in F, a finite field. Show that the only subfields of F are F itself and this smallest subfield consisting of only the zero element and the unity. At first glance, it seems like a problem that should be very simple, but we don't immediately see how one can get a solution. But the solution is actually quite simple if you proceed like this. Let L be a subfield of, the nature of this number will give you a clue. But if L is a subfield of F, then the non-zero elements in L form a subgroup of the non-zero elements in F under multiplication naturally. That is, this system is a subgroup of this since the latter group, that means this one, has order. The original field has order 32, it has one less element, so its order is 31, which is a prime. Lagrange's theorem from group theory, of course, that's understood, implies that the order of this subgroup, that is the order of the underlying set, is either 1 or 31. Because in this order, by Lagrange's theorem, this order has to divide 31, so it will either be 1 or 31. Correspondingly, okay, so when the order of this is 1, there is only one element in this subgroup, and what should that element be? It should be the unity in F, that is the unity 1. Now along with that, if you consider 0 also, then L will be this, and if the order is 31, then L minus the L difference 0 should be equal to F difference 0, and in that case L has to be equal to F. So we are going to write this directly at once. Correspondingly, we have or L equal to F. So that's just it. So it's in fact an application of Lagrange's theorem from group theory. Next, suppose that F is a field with 27 elements. Show that for every element A in F, 5A is the same as minus A. Okay. Now note that the number 27 is the cube of 3, and we already know that orders of finite fields appear like that, some power of a prime number, and that prime is in fact the characteristic of the field. So in this case the characteristic of the field will be 3. Since F has (27) elements, its characteristic is 3. So for any element A in F, 3A is equal to 0, naturally, because that's what characteristic is. This implies six A is also equal to 0, and so 5A is equal to minus A. So that's how we get 5A equal to minus A. And there is one more in this set of exercises, which is the last one, the 70th one. Let R be the set of all 2 by 2 matrices of this form: A minus B, B A, where A and B are coming from the finite field Z7, consisting of all the integers modulo 7 under the operations of addition and multiplication mod 7. And this set is being considered along with two operations with the usual matrix addition and multiplication. And modulo 7 addition and multiplication of the entries. That's because if you try to add two such matrices, then the entries have to be added, corresponding entries, by the definition of matrix addition. That entry addition is addition modulo 7, because the elements are also coming from that system. And if you multiply two such matrices, then the entries need to be added as well as multiplied. So there you are again going to use mod 7 addition and multiplication from this system. So under these two operations, we have to prove that R is a commutative ring. So that is the first job. Then how many elements are in R? That's the second thing we have to answer. And then, is R a field? That is another question. And finally, what happens if the entries are not coming from Z7 but Z5 instead? If Z7 is replaced by Z5, what happens if these things are done? The first part is absolutely straightforward and routine, but still let's go through it. Let A minus B be A, comma, C minus D, DC belong to R. Then their sum is, we already know what the sum is going to be. But the important thing is to carefully go through the calculation and do not forget that the entries are no longer real numbers or complex numbers, but they are coming from finite fields, that is this field. So this is A plus C minus B minus D, so minus of B plus D, B plus D and A plus C. So this matrix again has that form that we have in R, so this belongs to R. But there are some subtle things that should be noted carefully. You see, we are adding minus B and minus D, and in doing so, we have written minus of B plus D. Is it justified? Because now these are not real numbers or complex numbers. It is justified. That's because this system, under the addition modulo 7, which I am just simply denoting by ordinary plus symbol, is a group. And in this group, this equation, if you write using multiplicative notation, would look like this: B inverse D inverse equal to BD inverse, where the binary operation plus, here we haven't written anything, that is multiplicative notation. The inverse of B is actually minus B, the inverse of D is minus D, and like that we have. This equation is not true in a general group, but it is true in an abelian group, and this is an abelian group. So that's how there are some things, subtle things that you have to look carefully. But again, now it's okay. So this belongs to R. So we at least know that R is closed under this operation. That means the operation is a well-defined binary operation. addition of matrices is commutative and associative. Okay, but why? That's because these properties of addition of matrices are a result of the corresponding properties for the addition of the individual entries. Now, is our addition commutative in this system? Yes, because it's an abelian group. Is this addition associative? It is, because again it's a group, that's why. So that's why we have this thing. The matrix in R, don't forget to mention this, okay, because this means these are not ordinary real numbers, 0, acts as an additive identity, obviously, and the matrix minus A B minus B minus A in R, this will also naturally be in R, acts as an additive inverse of this matrix, this element in R. So, R is an abelian group under matrix addition. Next, we calculate the product of those two matrices. A minus B, B A. Is it A minus? Yeah, should not make mistake. C minus D, DC. If we calculate this product, then we get AC minus BD. A times minus D plus minus B times C, that means minus of AD plus BC, then BC plus AD, that is the same as AD plus BC, and minus BD plus AC, that means AC minus BD. So again, clearly it has that same form, belongs to R. Also, because we are calculating this product, let's also calculate that same product but with the order changed. AC minus BD minus BC minus AD, that is minus of AD plus BC, AD plus BC, and minus BD plus C, that means AC minus BD again. So you can see that they are actually equal, this times this and this times this. So R is closed under matrix multiplication which is commutative. I think I need a little ink, just a little bit. Now we are almost there. Also, matrix multiplication is associative and is distributive over matrix addition. Now you may be thinking that I am just simply going on writing these things as if I already know that these are true. Yes, I know these are true, you also know these are true, but in order to see why they are true, there is in fact no need to carry out the multiplication again. And again I am saying because we have already done these things for matrices with real entries. And there we saw that the things they work out, they are true. Does it mean automatically that the same thing will be true here? Yes, because there also we defined matrix addition and multiplication in a particular way. Here also we have defined them exactly identically. The only difference now we have is that the entries are not real numbers, but the entries are in fact coming from a field, a finite field, and the real numbers also form a field. And do not forget that in verifying these things we only used the field axioms that the entries satisfy. So there also we had the real field, here we have the field Z7. Same thing, we haven't used anything special about the real numbers being real numbers. They are just field elements and they satisfy those field properties. Here also these are field elements, they satisfy exact identical field properties. So that's why these things here also will be true. So that means we have in fact proved that R is a commutative ring. So this is the boring part, but the interesting part now it will come. So R is a commutative ring. Okay, what else was asked? How many elements are there in R? Since the matrices in R are of the form A minus B, B A, where A and B are coming from Z7, and that's it. There is no more restriction on these matrices. We see, we are not looking for a group under multiplication. We are looking at matrices that form a ring. That's it. So in particular, what I am saying here is that we are not considering non-singular matrices. We are considering every matrix that you can possibly get with the entries coming from Z7. So A and B, each one of them can be chosen independent of the other, and each one will have 7 options. Corresponding to each option of A, you have 7 options for choosing B. So the number of elements or the number of such matrices is 7 square, that is 49. Right. The next thing that has been asked is whether this is a field. Now, in order to see that, okay, what is it that you have to show if you want to show that this is a field? That every non-zero element should have an inverse. Is that going to be true though? You can think of 2 non-zero elements, say, yeah, this can be shown very easily that it will not be a field. Not directly using the definition itself, but using the fact that every field is an integral domain and hence lacks zero divisor. Here, however, it is very easy to produce zero divisors like this. Let me just see it. Okay, say you have 1 0 0 0. This is a non-zero element in our ring R. If I take 0 1 0 0 and calculate their product, what shall I get? 0 plus 0 0. Oh, I am having 1 here, no? So let me change this to 0 and this to 1. 0 0, we are still having 0 here. 0 plus 0 0, 0 plus 0 0, and 0 plus 0 0. So product of 2 non-zero elements has given me the 0 element, and this does not happen in an integral domain and definitely not in a field. So that's why it's not a field. And you can see that this same thing will be true if we replace our Z7 by Z5, because there also we have these things 1 and 0. So that's why, let me write it properly. R is not a field since the non-zero elements 1 0 0. Oh, wait, hold on. Oh, what the hell? I forgot totally the form of the matrix, right? Oh, then okay. No, it won't come like this. What I was thinking is totally wrong. Instead, let me just think of the inverse of this matrix itself. We have a formula for calculating the inverse of a 2 by 2 matrix, right? And according to that formula, inverse exists if and only if the determinant of the matrix is non-zero. This is true regardless of the nature of the entries. It does not matter from what field the entries are. See how foolishly I did that, but this is very common in mathematics. We should not get carried away like this, but we do that often. We have to come back and rectify ourselves. So what I am saying here is that the inverse of this matrix will exist if and only if the determinant is non-zero, and it does not matter whether the entries are real or complex or coming from some other field. Okay, this is the theory. So according to that theory, the inverse of this matrix will be this. Minus b over a square plus b square and a over a square plus b square. You can check this, you can verify this by calculating the product of these two. You will get the 2 by 2 identity matrix or unit matrix. Now the question is this: if this is a non-zero matrix in R, is a square plus b square non-zero? Because if it is, then being an element in the field Z7, it will have an inverse, which is the reciprocal. Reciprocal means it's multiplicative inverse, and that will give you this inverse matrix. But if for non-zero matrix and hence corresponding entries, also you get some 0 a square plus b square, then inverse will not exist. And that's where the difference between Z7 and Z5 will come into play. So let us write this part like this. For non-zero this element in R, we have, so non-zeroness means what? That at least A is non-zero or B is non-zero, that is, they are not simultaneously zero. And this is a place where again we are prone to make mistakes. That's because we may again think that because A is non-zero or B is non-zero means A square plus B square is non-zero, but these are not real numbers. In Z7, this implies A square plus B square is non-zero. In Z7 this happens, but this is only my guess. Okay, I haven't actually verified that this is the case. This is only my guess, so you have to verify it, and you can verify by going case by case. It may seem like a very time consuming task, but once you see uh, one or two things, that is, you take values of a and b, you will see that a square plus b square most likely will never be 0 with these two conditions. So in Z7 we have exactly the same thing, just like what we have in the system of real numbers. So the inverse, and let's write the expression for the inverse. Here we have D. You can, by the way, see that the determinant of this matrix is a square plus b square. Exists. So R is a field. I have in fact left out one part in showing that R is a field, namely that there is a unity in R, a unit element. But that you know what it will be, 1 0 0 1. That also belongs to R and it acts as a unity. Okay, so in this case R is a field, but keep in mind, again I am saying this is only something that I believe is true, because I believe that for at least A or B non-zero we have this, but please verify it and make sure that what I have guessed is correct. But now if we replace Z7 with Z5, then this will not happen. This will not happen means other things will happen. For example, the system R is still going to be a commutative ring. The number of elements will differ. In this case it will be 5 square, that is 25. There we had 7 square. Then R is still a commutative ring, but with five square equal to 25 elements. Now for the non-zero element 1 minus 2 2 1 in R, its, let's just mention the word, its determinant is 1 square plus 2 square, but that becomes 5, and in Z5 5 is equal to 0. So you see that despite having a non-zero matrix, the determinant is 0. In fact, both the entries are, all the entries are non-zero, but the determinant is 0. So this has no inverse. No inverse means no inverse under multiplication. That's understood from the context in R. So in this case, R is not a field. Actually, this difference stems from the nature of these primes 7 and 5. R is not a field. The nature, I was saying this because 5 is a prime that is congruent to 1 modulo 4, and there is a result in number theory that says that any such prime number can be expressed as a product of two squares of integers. For example, 5 is expressible like this. On the other hand, 7 is congruent to 3 mod 4, and there is again a result in number theory that says that no prime of this form is expressible in this manner. So that's where we have the difference. But anyway, that is the solution, and this current section is over. So in the next ring update on Gallian, we are going to start a new section, the next one. And let me just end the video here itself. And tomorrow also we have our usual analysis upload. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.